Hello everyone, I am Emad Ehsan. I am a Google developer expert for Pakistan, and this talk is about using Google OR tools and maps for route optimization. So just recently I had the experience of working with a startup in Lahore that does fresh goods delivery to shopkeepers. And Lahore is a really populous and old city. And if you could look at closely at the photo of the map, you can see most of the streets are close-ended. So it's really difficult to navigate in such a congested and most of the times undocumented area. But since Google Maps has covered everything. So most of the streets are on Google Maps, and they were facing the challenge of optimizing the route for delivering the goods daily to the shop owners. And there were a lot of options to select from. So usually the top Silicon Valley startups that work in route optimization and delivery domain, like OnFleet and Routefic, are usually not considered as a viable option because they are really expensive compared to for the startups working in developing countries and like in Pakistan, India, and also probably most countries in Africa. So we ended up for the time we ended up relying and on a really cheap solution that would use Google Maps behind the scene for optimizing the load and the route that each vehicle has to carry and follow to deliver the goods. And that uh, inspired me to look into what actually happens behind the scenes on route optimization. And before that, I did not have any experience in optimization algorithms. So, and also since the start of COVID, there have been a lot of volunteer projects trying to be helpful with all the COVID-19 situation. And as Bill Gates also mentioned that we'll probably have the vaccine next year, but we can start the efforts regarding logistic efforts probably regarding vaccine delivery to dangerous and even probably remote areas right now. Those efforts, in order to scale those efforts, we have to start thinking about the logistics problems right now. So there was also an inspiration about probably building some open source tool with a couple of friends that could do route optimization not only for in urban areas, but it could also probably capture the routes that are only feasible for motorcycles and in rural areas where some really remote areas where you do not have access to fuel, so usually vehicles cannot even go there. So thinking about that, we I I was inspired to look more into what happens really behind all the logistics of doing route optimization. So I stumbled upon traveling salesman problem, and it is a classic algorithm studied in operations research or integer programming. So these are the domains of mathematics and computer science that deal with optimization algorithms. So traveling salesman, it turns out, is a classic and comparatively a basic algorithm, and it the most popular variation of traveling salesman tries to find the shortest path to visit all the cities or all the locations in a closed path. And there are also variations where you visit all the cities but in an open path. So the solution of both problems look entirely different. So the main data that is the input data required for solving traveling salesman problem is called the distance matrix. It's a 2D array of containing the distance between all the cities. And for example, the table in this slide shows the distance for a few Chinese cities that I calculated for a cycling route actually. But here on the left, if the cities are listed on the left, if you traverse to the table and towards the right, you get the distance from the city on the left to the city on the top. For example, Xi'an is 1724 kilometers away from Dunhuang. And in order to calculate this distance, Google offers distance metrics API that are part of Google Maps platform. And you can use these REST APIs to calculate the distance between the cities or even the locations within the cities using Google Map, Google Direction API. So here you simply do an HTTP call, you provide your key and you tell it the origin of the city, also the origin locations. So the cities for which we want to calculate distance metrics. So in this slide, the origin cities would be the cities listed on the left, and the destination cities would be the cities listed on the top. They are the same cities, but we want to calculate the distance from every city to every other city. And this is the major input that we need for solving traveling salesman problem also, and also for route optimization. So we could take every possible way, and that the Google searches about traveling salesman problem led directly to Google OR tools, and understandably they have done a great job with the SEO as well. So you can go to developers.google.com/optimization. Type of optimization problem. From the stock sheets, you can model that problem really easily with the help of Google OR tools, and they come in Python, C++. You can model your problem in Python, C++, Java, and C#. So all that are there are all integer values. Of course, the software that finds the optimum or feasible solution for us, and the variables. So, for example, for the photo on the right, the variable would be the the values required to describe the shape. So they could be the coordinates in 3D system, and the variable could, and the objective. Our objective could be, for example, find the point that is at equal distance from all the edges, all the vertices of the shape. And the constraints would be probably you could let's say the constraint would be that the point cannot go outside the shape of this object. So if we can model this type of problem using OR tools APIs, OR tools would be able to find a really optimal solution. Of course, there are approaches. The traveling salesman problem and other optimization algorithms. Is the decision are the decision variables actually contain the output of your data. So defining decision variables the right way is crucial because they are used by the solver to find the optimal solution. And for the traveling salesman problem, a decision variable could be a 2D array containing ones and zeros. And let's say that 2D array contains ones at the places that are red and zeros at all other places. So the solution of our traveling salesman problem would be take the route. So we have to read this from left to right. So take the route from Urumqi and the distance highlighted points to Xi'an. So we go to Xi'an. From Xi'an, and the constraints are the rules that must be respected. To, for example, for PSP, all cities must be visited and a city must be visited only once. So the second constraint is used in the most common variant of traveling salesman problem, but there are some other variants that are lenient on this rule where you want to find the minimum path no matter if you have to repeat the city. And the objective is, of course, the goal of your program. So for PSP, it is to minimize the distance that you have to travel. And in a traveling salesman problem, the distance is usually traveled by just one vehicle or one unit. I wrote cyclists here because actually I took this slide from the work I was doing on optimizing route for cyclists. So uh, that brings us to vehicle routing problem, and the most basic vehicle routing problem deals with delivering goods from the depot go down to the customer locations, and you have multiple vehicles in this case, and the vehicles have go out from the depot and they have to come back to the depot. If you reduce the number of vehicles in vehicle routing problem, then it becomes the simple case of traveling salesman problem, where there's only one vehicle visiting all the nodes in uh, while traveling the minimum distance. So for this problem, uh, I took this diagram from Google OR Tools website where they describe the vehicle routing problem. And so let's say we have the depot that is at 0 kilometers from itself. So, but all the other nodes that are listed, those are the customers that are in are at the the number that the integer value that the written on them, that's how far they are from the depot. And let's look at some code. So for this simple vehicle routing problem, here I am using Google Code app to run the code online, and here you just need to install OR tools. All the other libraries are already installed for you, and we do the necessary imports. The most important is the PyRap CP, which is the CPSAT solver by OR tools for solving weaker routing problem. And in the traveling salesman problem that we discussed, there are a lot of ways to model that problem using OR tools, where you describe your decision variables, you describe your constraints, and you also describe your objective. But in the case of a weaker routing problem, Google provides a solving the root optimization problem. And here you specify the input that we have specified here. This is the distance metric, the major input. So it specifies that table in the shape of a 2D array, and contains the distance from all the cities to themselves and other cities. And we also specify in our variables the number of vehicles. So in this case, they are 4, and the index of the V2, which is 0. So uh, the first row contains the distance of D2 from all other nodes, and the rest are the distances of the nodes that we specified. They are in that order. And once we have specified our distance metrics, we have the option to control the way our input will be presented. So we define a print solution function, where we take the data manager routing solution, these variables. So the manager is a variable that is part of the CPSAT solver for vehicle routing problem, and it converts the nodes from Python integers. So in Python we have nodes as integers, and it converts them back and to the format that is used by the solver. Here we are specifying the uh, information about how to print the solution. The actual code that does the root optimization is here. So here we are getting the data model that we just saw above. It contains the distance metrics plus the information about number of vehicles and the depot. So we create a routing manager, and we provide it the data. And you can see here we have built-in methods just for solving VR routing. And we register a transit callback. So the task of this callback is it takes the node indexes in the format that are specified by the set solver, and it converts them in Python index integers, and we use that to extract the distance for the nodes in which in between which the distance was requested. So this function will be called multiple times by the solver while trying to find an optimal solution for the problem, and the solver would provide the indexes between which it wants the distance, and using that distance it will try to find an optimum solution for root optimization. Here we register that callback, and we set the R cost evaluator of all vehicles. So this is the function in which we so this is the formats that is written in the documentation about how you specify the transit callback. So the distance callback that provides the distance between cities, that is eventually registered as the cost valuator. And the dimension, here we are adding the distance dimension. So dimensions in this route optimization solver are the variables that accumulate over time. So you can think of them as, so let's say when you are considering the distance, so and a vehicle has to visit 5 nodes or cities or locations. So once it visits, it goes from city A to B, and then from B to C, the accumulative distance would be the distance between A, B, and the distance between B and C. So distance, another dimension in the case of the optimization algorithms would be the time. So when we are solving time critical vehicle routing, and for that we use time as a dimension. So these are these are the variables that accumulate over time, and we are looking to optimize, find the minimum possible values for these dimensions, so we could do route optimization effectively. And here we set that dimension, and so first solution heuristic is being set here. So the first optimal solution that is found, we are specifying to the algorithm that return that. And here, once we have found the solution, we are passing that to our print function that prints them in this fashion. So I'll share the link to this Google Colab. All of the code is actually taken from the OR tools documentation, and let's visualize this in slides. So this is for that problem. This is the solution that was written by the solver. So looking at it gives us a pretty good idea that probably it was able to find a solution where nodes that are uh, near each other, they would be assigned to similar vehicle. But that is not always the case. Sometimes the solutions are not as perfect. So you have to keep running the program furthermore, so you don't rely on first solution heuristic. You let it run a little longer as well. The second variation of vehicle routing problem is usually the capacity constraint, in which we also look at the demand. So the demand of that is to be delivered to each node. So for this diagram, and for this example, let's say the load that we have to carry to each customer is in kg. So we are only dealing with, so probably even if the load has different size, if it can fit into a vehicle or not. For this variation, we are not interested in that. We are more interested in probably the weight dimension. So um, let's look at how we would do that with uh, the solver. So same way we are going to define the distance matrix. So because we are looking to optimize the distance, but we are also looking for a way to optimize the capacity that is to be carried to each customer. So this demands variable, this is an array, a list that contains, let's say in kgs, or probably metric tons, how much goods are to be delivered to each customer. So then so if we look at index 3, the that customer asks for probably 2 metric tons of the goods. And we also define the vehicle capacity. So the task assigned to each vehicle, the load assigned to each vehicle must be less than or equal to its capacity. And for this too, we have 4 vehicles. Uh, Here we define the solution printer, but we are more interested in looking at how we define the capacity constraint. So the distance callback is similar to the previous variation, but we also have a demand callback where we give the index of each node or each customer, and it returns the load that they requested. And we register that demand callback with the solver, and here we again set the first solution heuristic. So find the first solution cheapest path arc, meaning find the cheapest find the minimum distance. And I am not a lot educated on guided local search. I am pretty new to optimization algorithms, but so one thing that we might want to look here is that here we are giving it 0. So even if a vehicle is assigned, so in the test runs, I think it was regarding that even if a vehicle is not assigned anything, any task, that is okay. So you do not have to give assign the load to every vehicle. So using the solution printers, the output provided by the routing solver looks like this. So I'm not I'm showing you the previous output, but once I share this, you can run and check the data live, make changes to it. So here we start from node 0. This is vehicle 0. So we start from node 0. We have we take 4. We go to node 4 and we carry 4 metric tons. We go to 3, and till 3 we'll be carrying, if we were to visit just node 4 and 3, we'll be carrying 6 metric tons. And if we are to also include node 1, we'll be carrying 7 metric tons. And so the solution would look for this problem like this. So here are we demanded to the solution that our demand constraint should also be respected. So this so in order to fulfill the demands, the solver has to prioritize dividing the load effectively. And here you can see the route does not look as perfect as it looked in the previous case, but it fulfills the customer demand in an optimum way. The next variant is pickup and deliveries. And this is sometimes also called the line haul and backhaul. in academia regarding vehicle routing problem, this variation of vehicle routing problem. And here we, with the help of arrows, we have shown from which node we want the vehicle have to pick up some load, and the arrow ends at the node where that load has to be delivered. So for this variant, let's look at our data model. And so same like previously, we have our distance metrics, and here we also define the pickup delivery. So this specifies the, you can think of each row in the story matrix as a pickup plus delivery order, and the values specify from which node we have to pick, and to which node we have to deliver that load. And this variation is a really simple variation that just involves pickup and deliveries. It does not involve dividing the load. And here we also specify the number of people are going to be four. And in order to specify this problem, once we register our distance callback, and we add the distance dimension, we so here we define the pickup and delivery order to the solver. So we take the nodes, we add. So here we are adding pickup and delivery, and here we are giving the information of. So you can see here routing dot add pickup and delivery. It's a built-in function. So they have provided the complete APIs for this variation, and we give it the index of. Is there any question? Okay. So we give it the index of the pickup location to the delivery location, and here we are letting it know that for a vehicle that a single vehicle has to carry this pickup and delivery order. So we are adding the constraint that if vehicle B picks up from node 1, vehicle B must be the one dropping that load to node 6. So that the load can't be swapped or something. And here we are also adding constraint that if it's covered till the pickup point is reached, must be less than the cumulative distance covered till the delivery point is reached. So this ensures that every route, any route does not, suggested by the solver, does not contain some route where we visit the delivery location first and the pickup location afterwards. It must be the other way. So the pickup location first and the delivery location must come afterwards. And also here we are defining the first solution heuristic. And for this variant, here's the output given by the program. Let's see it visually here. So you can see each vehicle that is assigned the tasks. So the same vehicle is responsible for delivering. If it picks up from from a location, it delivers it to the location for that order. So let's focus on node 1, 6, and 7, 8. You can see we have to take something from node 1 and deliver it to 6, and same for 7 and 8. So the vehicle highlighted, the route took by vehicle highlighted in green, it goes straight to 7, node 7, then it goes to node 1, and from both of these locations it picks up the load, then it visits node 6, drops the load picked up from location 1, and then it visits node 8, drops the second node. So a location can, so a vehicle can pick multiple loads and can drop them simultaneous one by one. So it is not, it is an efficient route. So from a really basic solver that usually are, for example, I was working with a solver that was not able to do it. It would pick from one location, drop that order first, then it would go to the pickup location for the other order. And the third and the fourth and last variation that we'll be looking is the time window constraint, and it is very similar to distance distance constraint, the very simple variant of traveling sales, vehicle routing problem. But here we, because here we there we optimize for distance, and here we optimize for time. But another one other restriction, a constraint added in time window VRP, is that we have to visit those locations under the time period mentioned by that node. So let's look at the code for it. So unlike the previous problem where we had a distance metric for the vehicle routing problem, with time window we have a time matrix, and we also specify the window between which those nodes must be visited. So the vehicle has to depart from the repo from in under the interval 0 and 5, and here we are specifying that for node 1, the node 1 must be visited between 7 and 12. So you can think, here we are specifying the time interval as time. You can probably think of them as hours of the day. So between 7 a.m. till 12 p.m. we have to visit this node with the load. And again, we specifying 4 vehicles, and the depot is node 0. Solution printer, but let's move to the code for time window VRP. So before we specified, we used to specify time, distance callback. It would return the distance between two nodes. Here we specify the time callback. It returns the approximate distance. So not approximate, the distance mentioned in the time matrix. It returns that distance for the two nodes, and we are registering this transit callback here, and adding this as this dimension as time dimension, and here we are allowing 20 units of waiting time, and maximum. So this, in the case of if you specify it maximum allow waiting time to be 0, for the case of distance, it would allow the vehicle to, even if a vehicle is not assigned any task, that would be okay. But for the second actually the third argument, where we specify the maximum time per vehicle. For distance dimension, we specify here the maximum allowed distance that we want our vehicles to travel. So that distance cannot be exceeded. So in this case, this time cannot be exceeded. The task should be complete in these unit of time, and we set that dimension. And add here we add time window constraint for each location, but we exclude the depot location. That's because those vehicles have to return back to the depot after completing their tasks, and the time window for depot is 0 to 5, but the time would be more once we get back to the depot. So we exclude that, and then we add. So then we add time window constraint for each node each vehicle start node. So the time that it has to reach, and the time that it has to leave from that node. So here we are specifying that window, and next we specify the instantiate. So add variable minimized by finalizer. We add the time dimension. So this cumulative time dimension must be minimized for each vehicle. But we are also specifying both the start and the end. So because we have that range, and then we add the first solution heuristic, and same way we get the solution. And so the solution gives which nodes must be visited by each vehicle, and the time window between which those nodes must be visited for it effectively reaching those nodes. Here I was experimenting with trying the nodes on the graph. I will hopefully complete that. I'm going to share the link to this collab in the slides, and I'll probably let change things. I'm going to paste it in the chat.
Yeah, so you can see that there are a couple of questions in the chat if you want to take a look at those and answer them now.
Yep. So special demo, and how does it look on the map? So for map, I do not have it right now, but we can probably look at a few pros on the Google Maps. So route optimization. Probably let me show you the very simple variation from my previous talk that I did just on traveling salesman problem. And so this is a very simple variation of vehicle routing problem, where we visit the nodes, and but we visit them using only one vehicle. And so the simplest form of vehicle routing problem is simplified to even more here, and we use, and we are not returning to the starting location. I do not have the visualization for multiple vehicles on the map, but probably this will give you an idea. I calculated this route using the maps the Maps Distance Metrics API and the Maps for a cyclist group that is planning to travel on the Silk Road next year. So they'll be traveling from Xi'an, China, to Istanbul in Turkey, and the distance metrics that I show you there is also the one that was used in this. So probably this gives an idea about, because in real life the paths are not in straight line, they are passing through multiple locations, streets, highways, and a lot of other locations. Yeah, that would be it from my side. And yeah, so just last few words. If while designing a route optimization service, we we cannot only rely on our tools, we also have to build some other service on that. So for example, all the route optimization services like OnFleet, Routifix, and probably Token, they all use state-of-the-art mobile apps to track to travel locations, and they also add the capability to update the routes on the go. So if there is a pickup and delivery order while the vehicles are already dispatched, those orders can be assigned as well. And you also sometimes need the fleet management software. For further reading, I would highly recommend the Practical Python AI College book by Sergey Crook. It's a really great way to start learning optimization algorithms from scratch, and of course the Google developers documentation. I am Emad Ehsan on LinkedIn, and on Twitter I am E_Emad_Ehsan if you want to connect. That's it from my side.
All right, thanks a lot for your talk. I do have one question for you, one follow-up question. So you use a distance matrix API to get all of the distances between the locations. Does that distance matrix API take traffic into account? Can you specify a time frame when this has to happen or not?
Yes, so they do specify the time and the current traffic. They do take that into account, and they also take so Google has this awesome service called routing. It's part of the Google Maps platform, and here you can use this service to take real-time information about the route that you want to take. So, so the current traffic situation, also the distances, and those things. So it's available under as the routes under Google Cloud.
Okay, perfect. And so the matrix distance API, it's on the web, right? I can create some code that's going to call it, get a response from it. The optimization tools are all offline. Is there an online API for those tools? Meaning, could I build a solution where I just make calls to different Google APIs and build a solution based on that? Or would I have to mix some remote calls to the Google APIs and some offline stuff with Python like you did here?
So if I understood your question correctly, you mean that do we have to call the metrics API for every problem, or can all the calculation be done offline?
Well, can I do everything online or everything offline, I guess.
Oh.
Yeah.
So for the second question, doing everything offline for real world problems is not possible because uh, so let's say you are solving the problem for Lahore and there is no map in the world that has documented Lahore as good as Google Maps. So for every different order that comes from any other town, you have to use
You need the
the metrics
data.
API to
Yeah.
get the distance. Yep. So, I think that Google does not provide the complete solution themselves for doing the vehicle routing. So, all the services that are built usually rely on the mix of distance metrics and these routes service part of Google Cloud.
Okay, perfect. Do we have any other questions from the audience? Looks like we are all good. So thanks a lot, Emad, for your talk. That was very interesting. And I didn't know that there was all of these optimization APIs now. I played with the routing a little bit years ago. And back then, it was just a distance matrix API. There was pretty much nothing else. So knowing that now they have all of these different things that take into account constraints, so all of the different examples you showed, that was pretty interesting to learn about. So thanks a lot for your time. Thanks for giving us this talk. And we are going to publish it on YouTube very soon. So thanks again.
Thank you for having me, and it's been a pleasure preparing it and presenting it. So thank you.
No problem. Thanks a lot. And thanks everyone for attending tonight.